But first, we have a talk from Cody, who's telling us about a project he did over the summer as an intern at Oracle. So thanks, Cody.
Yeah, thanks, Rob. Can everyone hear me okay? All right. So yeah, thanks for letting me speak. Thanks for Jeremy and Rob for organizing this conference. It's great being here.
Maybe slide up, maybe. Yeah.
All right. So yeah, this as Rob mentioned, I did this work as part of an internship at Oracle Labs. John Tristan was my mentor, and Joseph Tassarotti collaborated with us from Boston College. So the origins of this project was that John had a machine learning algorithm that they had developed at Oracle, and they wanted to prove, and he had a pencil and paper proof about certain properties of that algorithm. Coming from a formal verification background, he started to wonder what it would take to have a machine checked proof. And he's not alone. We're starting to see an increasing trend in machine learning systems which on paper are proven to have certain guarantees, but because they are so critical and we're starting to see machine learning everywhere nowadays, it's important that we have machine check proofs of the claims which they drive. I'm by no means a machine learning expert, and so I was told that these two papers were of the kind I just mentioned, where they had pencil and paper proofs of properties, and yeah. So verifying these algorithms are different in the sense that they require quite a bit of mathematical prerequisites, because the claims which you make about some of these algorithms are about their probabilistic behavior. And unlike cryptographic algorithms or randomized algorithms, we need to support probability with continuous numbers and distributions. And the literature is not always as rigorous or detailed as we like. And technical conditions on lemmas are often omitted. Some hypotheses are not even mentioned, and some serious details are fully skipped. So verifying these algorithms is a bit of a challenge. So at Oracle, what we did was we took the simplest possible example we could think of, something which every classic machine learning textbook on statistical learning theory mentions at the very start. We call this the decision stump learning problem. I'll say more about that in a second. And we proved a generalization bound about this problem in Lean. Most of these textbooks start off with this and use this as a motivating example to build on general more theory. So the goals were to exercise libraries, see if we needed anything else, and we wanted to use this as a warm-up for more advanced results, possibly aiming at the fundamental theorem of learning theory. So this is the problem. So the black line is the non-negative reals. Ignore the arrow on the left. And these points are non-negative real numbers. You label them with two colors, the blue dots and the red X's. And the goal is you are given these points as input, and given enough number of them, you need to specify an algorithm to learn a boundary which separates these 2 points. That boundary is given to you. Well, it's not given to you, it exists, but you need to approximate it with the data you have. So this is the dotted line is the unknown boundary value, which separates both of these classes. So given this, a reasonable thing to do would be to, so given these points, a reasonable algorithm which you might think of is to return the largest linear example, that's a circle, and use its value as the boundary. And it turns out that this works really well in practice. We can prove that given enough number of points like this algorithm can be made to have arbitrarily small error with a high probability. So from now on, so formally the setup is as follows. X is the non-negative real numbers. Sorry about the notation, but and the concept class of decision stumps I call is a subset of functions from the non-negative reals into 0, 1, which take a non-negative real number x and return the indicator of whether x is less than or equal to c for various non-negative real numbers c. So every such function is a red and blue labeling. Now, because this function is determined completely by the cutoff value c, from now on I will identify the function with the cutoff value. So there is a c given to you in the previous problem, which is represented by the dashed line, and the objective is to learn that value c. So informally, the theorem, which is the motivating example, is as follows. So given the set of points, the blue and red points, there is an algorithm A and a sample complexity function, which is just an integer, m, such that for any distribution mu over x, this is important, and a c in the concept class, which is the dashed line, and for epsilon and delta, when we run this algorithm A on enough number of points, n, which are greater than the complexity, on samples from mu labeled by c, this algorithm returns a hypothesis, a candidate function, which approximates this function c very well with a high probability. So it's probably approximately correct. So this is the paradigm of PAC learning. Now, because I've already said this. So I want to now sketch a proof of this statement, which is what we tried to formalize. Because mu is a distribution, a probability distribution on the non-negative real numbers, the error, which is the quantity in question, this quantity, now I identify with it's simply mu of h and c, where h and c are the cutoff boundary values associated to the functions h and c. Okay, so now this is the quantity which I have to bound. So the sketch of the proof is as follows. So given mu and epsilon, consider n random samples which are given to you with labels li according to the concept class or cutoff value c. The learning function now, the algorithm, you run the algorithm on these points and it returns the greatest blue value. And if I have that, if I have mu of 0 to c is less than epsilon, then the bound on the error is trivial because mu of h and c is less than or equal to mu of 0 to c by monotonicity. So we assume that the error, we assume that mu of 0 to c is greater than or equal to epsilon. So the proof now proceeds as follows. Find a theta such that mu of theta to epsilon is exactly equal to, mu of theta to c is exactly equal to epsilon. And let's call that interval I. I is the number from theta to c, the interval theta to c. Now, if the boundary point h, which the algorithm returns, is inside theta to c, then we have by monotonicity that mu of HC is less than or equal to epsilon. So the error is bounded by epsilon. So we are done. So now for the error, if mu of HC is greater than or equal to epsilon, this means that theta lies inside HC. Now by the choice of H, which the algorithm A returns, this means that none of our samples Xi came from I, because the mass of the interval I is epsilon, the mass of its complement is 1 minus epsilon, and so the points Xi are either on the left half or the right half, so they're at most equal to 1 minus epsilon. So the probability of a point Xi not belonging to this interval is at most 1 minus epsilon. Now, because the points Xi were independent and identically distributed, the probability is at most 1 minus epsilon to the n. Using this, because we started with this quantity, and this is the quantity we needed to bound, by considering complement events, we can now bound the probability and get the desired bound. So, and if we choose m large enough, we can make this quantity less than delta for any given delta. Now, this was the proof which we adapted from textbooks, but if you were paying attention, you might notice a problem with this proof. The problem is that such a theta may not exist. Because we quantified over all probability distributions over the non-negative real numbers, such a theta may not exist. And it's not okay to say that we will just consider continuous distributions, because my collaborator tells me that in learning theory, they consider discrete distributions all the time. So it is important to include the case of discrete and even mixed distributions. And indeed, this is a counterexample to this proof. If we take mu to be this distribution, then the desired theta does not exist. So to fix this proof, the theta should be defined as follows. And we need to prove another fact about it, which was the most challenging part of the formalization. And once we do this, we fix the proof. And this proof has now been formalized. So yeah, and you can find the formalization at the GitHub link. So as I said, this proof was taken from machine learning textbooks, and nearly every reference we considered got it wrong. Some of them, I mean, the one on the right got it right, but they still omitted the hardest part. They just brushed it under the rug, saying it's not hard to see that this is true. But even like for our case, even if the proofs were wrong, the theorem is indeed true. But there are other results in these books which are wrong as stated. The problem with that is they omit technical conditions on measurability, and that is reasonable, because if you're a practicing ML person, you don't want to think about measurability. You just want to get work done. So it's reasonable. Now the challenge is, can we come up with an interface which can automate these tedious details about measurability, or if that is too much to ask, can we at least ask for a more a better way to organize these machine learning algorithms, the stages, and this is where, all right, before that, most of these machine learning algorithms come in 3 stages. You draw a random sample from labeled training samples, from labeled training examples. You run the learning algorithm on these training examples, and you consider the behavior of the algorithm on the classifier on test examples. Now, this is where the GD monad helps us organize this more efficiently. So yeah, before I begin, I want to thank Johannes for his libraries. I wish you write every library I ever work on. So the GD monad lets us rigorously formalize certain common informal arguments in probability theory. It also provides a natural denotational semantics for a subset of probabilistic programming languages. It also allows us to perform ad hoc notation overloading, which we know and love. If x is a random variable, we want to take the cosine of x without supplying the event omega and say you need to find the cosine of omega of x of omega. The GD monad allows us to do that. It also simplifies certain constructions such as the product measure, which I will go into. So first of all, what is it? Well, if Mies is the category of all measurable spaces together with measurable maps, for a measurable space in this category, let P of M stand for all probability measures on M. Now, I will proceed through a construction which makes P of M a measurable space. And to do that, I will introduce these functions tau f, which are defined as follows. And I call these the evaluation maps because if f is an indicator function, they simply take a measure to evaluation at the underlying set. Now, this P of M can now be equipped with the weak star topology, which makes all of these maps tau f continuous. And because it's now a topological space, I can consider the Borel sigma algebra on this, which now makes it an element of Mies. So P of M, the space of all probability measures on a measurable space, is also a measurable space. Now, P also acts on functions as pullbacks. So putting all of this together, I've now exhibited to you an endofunctor on the category of measurable spaces. Now, to make this a monad, I need to give you the bind and return. So the bind is quite simple. It just takes a point in a measurable space M and returns. There's only one thing you can return almost. The natural thing to return would be the Dirac measure on that point, which concentrates all the mass on the point X and is zero everywhere else. The bind is a little more complicated, but if you fiddle around with this for long enough, this is the only thing you can come up with. So, and also once you have the bind and a return defined as follows, you can check that the monad laws are satisfied. But the caveat is that the monad laws only are subject to measurability conditions. So this means that everything that the GD monad eats has to be part of the measurable space type class and lean. If it isn't, then it starts complaining that the thing which you just fed me is not measurable, I can't eat it. Okay, so how does this help us with learning algorithms? Well, once you have a bind and return, there's a natural do notation which you can associate to it, which I will now read as sample from mu as x and continue by f of x. So the three stages I mentioned to you before for any learning algorithm will now go as follows. I draw n points from the distribution mu and I store that in the in training. I run the learning algorithm on this training sample and I store the result in C. Now I draw m points from mu and call that test, and I return the score which compares the test to the classifier. So the cool thing now is you can reason about these three different stages, and at the end of it, because you obtain a probability measure, you can derive a bound on it overall. So this allows you to cleanly separate your formalization into stages, and at the end you can reason about it at one go.
So learn itself is
Sorry, I can't hear you.
learn itself, is it also probabilistic? Is it a distribution function?
Yeah. You need to make it return Mies of something. Yeah. Um, so yeah, this was the GD monad for learning algorithms. I quickly want to run through the GD monad for other constructions. So you could do things like this: draw x from a normal distribution with mean 0 and variance 1, and draw a point y from a distribution with mean 0 and variance x, and return the product x and y. You can also construct the product measure in a similar way. So using the GD monad, the theorem we proved in the paper went through like so, because there were so many different measures involved, there were so many probabilities involved. But expressing them in the monad made it much more convenient to derive a bound at the end. Yeah, I won't go through these, but f star is just notation for the push forward, and mu n is the n-fold product measure on mu. The GD monad can also be interpreted for probabilistic programs. Again, Johannes, thank you for explaining this to me. So the Kleisli arrows of the GD monad can be thought of as parameterized probability distributions, and the GD monad allows us to combine and sequence these probabilistic programs. But everything, unfortunately, is not so nice, because there is no generic measurable space structure on the function space alpha to beta. Which makes the evaluations map continuous. So this means that you can't pass around higher order functions from within a monad block. I think Johannes and Manuel have a proof of this in Isabel. So in conclusion, I want to say that there is a lot more stuff which needs to be done to formalize learning theory. And from what I see, it's going to be a struggle. And yeah, monadic abstractions can help conveniently structure formal proofs. So maybe there are other monads out there which will make our lives easier. I talked to, okay, that was a good time to do this connection. I actually mentioned this to Sebastian. I found a candidate called the tangent functor monad, but it doesn't seem like it's good. So maybe there are others out there. Thank you.
Time for questions. Johannes?
So, like textbooks on machine learning using them now?
No.
They should.
They should, yeah. I don't think pure mathematicians have heard of the GD monad, as far as I can tell. Yeah.
Nice sample of pure mathematicians, none of them has heard of it.
I'm not surprised. Yeah. I think it comes up naturally when you start to think of how to formalize these things, because otherwise they're just, I mean, you just throw them around and it works for mathematicians, I guess. Yes, yeah.
So one problem is that the Shuri monad is not a monad on type, but in measured spaces, so this means category. So
Yes.
the question is, for me, it would be, I mean, we have category theory and we have monad and category theory. So the question is, it would be interesting to use the category, the construction we have, and use these instead of the Shuri monad on types and measured spaces.
Yes, I did consider that, but I'm not sure how exactly it would be any different from doing it the plain old way.
I mean, it's a different issue is that you do not need to prove measurability as often as you have the category, any working categories, because it's just.
Oh, right, yeah.
There is a button to that with measurability. It's a measurability property and so on. And also when you prove,
But don't you have to prove that everything you work with is an element of the category?
yeah, at the beginning you put everything into the category and then you compose it. That's
Okay.
how it should work. But the question is if you have enough
Other questions? No? Okay. Okay, let's thank Cody again.
Thanks.